Hello friends, in previous lecture we have studied L2 class which contains real sequences xn such that summation of xn square less than infinity, and we also studied Square's inequality for L2 set. Today we will see Minkowski's inequality for L2 space. Okay, Minkowski's inequality. Inequality. If S is equal to Sn and T is equal to Tn belongs to L2, then S plus T belongs to, what is S plus T is equal to Sm plus Tn sequence belongs to L2, and summation of Sm plus Tn its square n equal to 1 to infinity raised to half is less equal. Summation of Sn square raised to half n equal to 1 to infinity plus summation of Tn square raised to half n equal to 1 to infinity. Now, since S and T belongs to L2, therefore, summation of Sn square n equal to 1 to infinity less than infinity, summation of Tn square n equal to 1 to infinity less than infinity. Okay. Now, for any fixed n, also by Square's inequality, summation of Sn Tn n equal to 1 to infinity converges. Okay. And summation of Sn Tn is less equal summation of Sn square raised to half n equal to 1 to infinity into summation of Tn square n equal to 1 to infinity raised to half. This is 2. Okay. Now, summation of Sm plus Tn its square n equal to 1 to infinity is nothing but summation of Sn square plus 2 times Sn Tn plus Tn square. Now, Sn square, summation Sn square is convergent, summation of Sn Tn is convergent, summation of Tn square is convergent. Therefore, their addition is convergent sequence. So, I can write summation of this equal to summation of Sn square n equal to 1 to infinity plus 2 times summation of Sn Tn n equal to 1 to infinity plus summation of Tn square is from 1 and 2. Okay. This is less equal. Summation Sn square n equal to 1 to infinity plus 2 times summation Sn square n equal to 1 to infinity raised to half, is it clear, plus into summation Tn square n equal to 1 to infinity raised to half plus summation of Tn square n equal to 1 to infinity by 2 again, by 2, is it right? But this is precisely equal to summation of Sn square raised to half n equal to 1 to infinity plus summation of Tn square raised to half n equal to 1 to infinity bracket square. Taking square root on both sides, taking square root on both sides, we get summation of Sn plus Tn its square n equal to 1 to infinity raised to half. This is less equal summation of Sn square raised to half n equal to 1 to infinity plus summation of Tn square raised to half n equal to 1 to infinity, n equal to 1 to infinity. Is it clear? Thus, result is proved. Result is proved. Is it clear? Now define norm of the sequence in L2. Norm. If S is equal to Sn, n equal to 1 to infinity belongs to L2, then norm of S sequence S is, S belongs to L2 is, norm S2 is equal to summation of Sn square n equal to 1 to infinity raised to half, raised to half. This is definition of norm. It is just like as a length. Okay. Theorem. For St belongs to L2, for S is equal to Sn, T equal to Tn belongs to L2. First, norm of S2 greater equal 0. Second, norm of any sequence greater equal 0. Second, norm of k times S 2 is equal to mod k into norm of S for any k belongs to R, and the norm of S2 is 0 if and only S is equal to 0, 0, 0. S is 0 sequence. Third, triangle inequality. Norm of S plus T2, norm of S plus T less equal norm S plus norm T. So proof. First, by definition, norm S2 is equal to summation of Sn square n equal to 1 to infinity raised to half greater equal 0. Second, norm of for k belongs to R, norm of Ks2 is equal to summation of Ksn bracket square n equal to 1 to infinity raised to half is equal to summation of k square Sn square raised to half. Okay. By taking n equal to 1 to infinity, k square raised to half is nothing but mod k, because we are taking its square root. Is it clear? So we will get this is equal to mod k into summation of Sn square raised to half, which is equal to mod k into norm of S2. And third, norm of S plus T 2 is equal to summation of Sn plus Tn its square 1 to infinity raised to half, but it is less equal summation of Sn square raised to half plus summation of Tn square n equal to 1 to infinity raised to half by Minkowski's inequality, which is equal to norm of S2 plus norm of T2, norm of T2. So thus all properties are proved. So in vector spaces, with help of, for given S and T, S plus T belongs to L2, then for S belongs to L2, K times S belongs to L2. So it must satisfy all axioms of vector spaces. So L2 is a real vector space on which we can talk about the norm. So it is norm linear space. It is norm linear space. In fact, L2 is the complete metric space. L2 is complete metric space. So it is complete norm linear space, and complete norm linear space is called as Hahn-Banach space. So you will come across Hahn-Banach spaces at MSc level in functional analysis course. In functional analysis course, so you are much more familiar with all those concepts which we will learn later. So next we'll take exercise 3.10. In that question 1, which of following sequences are in L2? Following sequences lies in L2. In that first, 1 upon log n equal to 2 to infinity. So for this sequence, for this real sequence, summation of Sn square n equal to 2 to infinity is equal to summation of 1 upon log n its square n equal to 2 to infinity. Is it clear? Is equal to summation of 1 upon log n its square, n equal to 2 to infinity. If I denote this by summation an, so for this series, an is equal to 1 upon log n its square is greater than 0 for every n greater or equal to 2. An is equal to 1 upon log n its square is greater than 1 upon log of n plus 1 its square is equal to m plus 1 for every n. Okay. Now 2 raised to n into a to the suffix 2 raised to n is equal to 2 raised to n upon log of 2 raised to n its square. Is it clear? So which is equal to 2 raised to n upon n log 2 its square. Is it clear? So which is nothing but n log 2 raised to n upon log 2 square into n square. And therefore summation of 2 raised to n a to the suffix 2 raised to n is equal to 1 upon log of 2 bracket square into summation of 2 raised to n upon n square. Okay. So this is 1. Now summation of 2 raised to n upon n square is equal to summation bn is series such that limit n tends to infinity of bn plus 1 upon bn equal to limit n tends to infinity of 2 raised to n plus 1 upon n plus 1 bracket square into n square upon 2 raised to n, which is equal to limit n tends to infinity of 2 raised to n into 2 into n square upon n square into 1 plus 1 upon n bracket square into 2 raised to n. This 2 raised to n get cancelled, n square get cancelled, and it approaches towards 2 greater than 1. Therefore by ratio test, summation of bn is divergent, and therefore from 1 summation of 2 raised to n into a to the suffix 2 raised to n is divergent by Cauchy condensation test. It's divergent. And therefore summation of n is equal to summation of Sn square is divergent by Cauchy condensation test. And therefore Sn is equal to 1 upon log n equal to 2 to infinity. This sequence then belongs to L2. Second example, if I take 1 upon e raised to n, is real sequence such that summation of Sn square is equal to summation of 1 upon e raised to n its square n equal to 1 to infinity is geometric series with ratio r is equal to 1 upon e square belongs to 0, 1, and therefore summation of Sn square is convergent. Therefore 1 upon e raised to n. This sequence belongs to L2. Is it clear? Question 2. Give an example of sequence Sn in L2 such that summation of mod of Sn is equal to infinity. Give an example of sequence Sn in L2 such that Sn in L2 such that summation of mod of Sn diverges. So Sn is equal to 1 upon n equal to 1 to infinity is sequence such that summation of Sn square is equal to summation of 1 upon n square is convergent series. And therefore 1 upon n belongs to L2 such that summation of 1 by n mod Sn is equal to summation 1 by n is infinity. That is, summation mod Sn is divergent. Is divergent. Next example, question number 6. Or if Sn belongs to L2, then prove that limit of Sn is 0. Next example. If S is equal to Sn belongs to L2, then show that limit n tends to infinity of Sn is 0. Solution. Since S is equal to Sn belongs to L2, therefore summation of Sn square n equal to 1 to infinity is convergent series, and therefore limit n tends to infinity of Sn square must be 0, and therefore limit of Sn is 0. Since if limit of Sn is L not equal to 0, then limit of Sn square is equal to L square not equal to 0. Okay. Thus result is proved. Next example, if n belongs to, if summation of mod n is less than infinity, if summation of mod n is less than infinity, then n must belongs to L2. Then n belongs to L2. Since summation of mod n equal to 1 to infinity is less than infinity, implies limit of n tends to infinity is 0. Moreover, there exists positive integer n such that mod n, this must be less than 1 for all n, must be less than 1 for all n. All n's are less than that, and therefore n square is less than equal to mod n for every n greater equal n. And therefore summation of n square n equal to 1 to infinity or n equal to n to infinity is less equal summation of mod n equal to n to infinity, less than infinity. Since summation of mod n is less than infinity, n equal to 1 to infinity, implies summation of n square n equal to 1 to infinity, this must be less than infinity, implies n belongs to L2. So as these terms goes on decreasing, that are very close to 0, so there must exist some positive integer n such that all n's have modulus value less than 1. So their squares must be less than mod n, their squares must be less than mod n. So onward that, if I take sum of that series, summation of n square lateral n term, it is less than infinity due to this. So with the discussion, we will stop our lecture here. Thanks for listening lecture carefully, and with this lecture our syllabus of real analysis 1 course is over here. If you have any doubt about any example from exercise, you can ask that difficulty personally to me. Thanks again.